We are looking at the knowledge area chemical change, and the topic is mass percentage composition. Right, mass percentage composition. Right, we need to ascertain the composition with respect to mass. Right, so what does it mean? Composition in terms of mass, we want to know what is the relative mass of the elements in a compound, right? So we can have, for instance, I could say, what is the gender composition in South Africa? That would mean I want to know what is the relative amount or the relative number of males to females in South Africa, right? Or I could say, what is the age composition in South Africa? And for instance, we may want to know how many people are above 60, how many people are between 50 and 60, how many people are between 6 and 18, so we have a sense of what the school-going population is, right? Or we may want to have a composition of how many people are employed and how many are unemployed. So composition gives us an indication of the relative amounts of what we seek to ascertain. Right, but we are dealing with a mass percentage, so the mass percentage composition is independent of the size of the sample, and it is an intensive property, right? We dealt with what an intensive property is, right? And the intensive property doesn't depend on, in this case, on the size of the sample, whether we have 200 grams of the sample or 100 grams of the sample or 50 grams of the sample. The percentage composition is regarded as being an intensive property, more or less like density. Right, the formula of a compound is already known here. So we know the formula of the compound, and its mass percentage can be determined. Okay, so we know the formula. We want to know what the relative masses of the respective elements are. So here we're going to have the formula of the compound, and we're going to determine the relative percentages. Later on, we will give you the relative percentages or the mass percentages of the element, and you will have to determine the empirical formulas. All right, so now, if we got mass percentage of element, that means we want the composition of a particular compound, right? So we want to know what is the mass percentage of the elements it's made of. So that would mean that over mass of element in sample, right, over the total mass of the sample, and we multiply that by 100%. Now, let's see the first one. If we're looking at, and we want to determine the percentage composition of Fe2O3, okay? So we want to know the relative percentages of these two. So what do we do? Okay? Firstly, we determine the molar mass of this compound. So we say M of Fe2O3, right? What is molar mass? So we know iron, so we say, all right, let's see what's iron, and we do that, and here we have that, and we say, all right, if we look at iron and we want to know what is its mass, and we find that its mass is 56, right? Oxygen, we know its mass is 16. Okay? Now, if we look at this, we say, all right, but we've got 2 of iron, which means 2 times 56, right? Plus 3 times 16, which gives us 112 plus 48, right? And that is equal to 160 grams per mole. Right? So 1 mole of this particular substance, right? Iron oxide is 160 grams per mole of that substance. But we want to know, of that 160 grams, how much is iron and how much is oxygen. So if you want the percentage of iron, you say, okay, that would be equal to, we know that we have 112 grams, all upon the molar mass is, right, 160, right? Okay, 160 grams per mole, right? Which then means, in this case here, times 100%, which says, okay, we've got, of the total mass of 160, which then gives us 70%, right? So we said, okay, it's a mass of the element in the sample over the total mass of the sample times 100%. Then we say, okay, oxygen, so we want percentage of oxygen, which would mean we've got only 48 grams of oxygen, right? There you see 48 grams of oxygen, and our total mass of the sample is 160 grams. Okay, times that, which then gives us, we got 30% of iron. Right, so what is this actually telling us? It's telling us, if I have a 100-gram sample of iron oxide, in that 100-gram sample, I will have 70 grams, which is iron, and I will have 30%, which is oxygen. That's what it's telling us, okay? So it helps to work out the percent composition, because you can bring it down to a base like 100 and say, okay, in a 100-gram sample, I know what percentages I have of each in terms of grams or kilograms or whatever you using. Right, now, next one says, determine the mass percentage composition of the following. Right, this is the mass percentage of testosterone. Right. And testosterone Okay, it's a it's a male sex hormone, right? And the formula for this is C19H28O2, right? That's the formula for that. But now we want to determine what the percentage of each of the elements are within that particular molecule here. So we say, okay, M of C19H28O2, right? Which is equal to 19, and we know carbon is 12. You should know that by now. And you should know that hydrogen is 1, and we have oxygen, which is 16, right? These are common elements, so by now you should know what the masses are. And that is equal to 228, right? And plus 28 times 1 is 28, plus that is 32, which in total is equal to 2, right? Which is equal to 288 grams per mole, right? But we know this whole sample has a mass of 288 grams. Right, but now we want to know what percentage is carbon in here. Okay, what percentage is carbon in here? So we want to know what percentage is carbon in here, then we say, alright, and that is equal to, we see here, right, that's 288, so 228, so it's 228 grams, right, upon the total total of 288, right, grams times 100, okay, and that, okay, we can say percent, and that is equal to 79.2%. Okay. Right. Then we say, okay, what percentage of hydrogen do we have here? Percentage hydrogen is equal to 28, okay, divided by 288, okay, times 100%, which gives us 9.7%. And then we want to know what's the percentage of oxygen in here, and that would be equal to, we saw oxygen was 32, so it's 32 grams all upon 288 grams times 100%, which gives us 11.1%. Right, if you add all these percentages up, that should add up to 100, okay. And what it is actually telling us that the male sex hormone, if you have 100 gram sample of it, you got 79.2 grams of carbon in there. And you got 9.7 grams of hydrogen, and you got 11.1 grams of oxygen. Right, so there you have that. Now let's look at the next one. If we look at now ammonium hydrogen carbonate, we say alright, we need to know the mass percentage in this one. So we say alright, M of NaHCO3, which is equal to, and if you look at the periodic table, you will see that it is 23 grams, right? So, okay, we know it's 23 grams. Now, let's first maybe do this so you know. Let's say we know that this is Na plus 1H plus 1 carbon plus 3 oxygen. Okay, let's do that. So this is 23, we know. Hydrogen is 1 plus carbon is 12 plus 3 times oxygen is 16. Right, so we know we have this, and we need to now determine the percentage of Na in here, which would mean we know we got 23 grams, which is 23 grams, right? Sorry, this gives us 84 grams, right, per mole. So we know that's per mole. So sodium would be 23 grams per mole. Hydrogen would be 1 gram per mole, the atom. Carbon would be 12 grams per mole. And oxygen would be 48 grams, right? And we've got 3 moles of oxygen, the atom. All right, so if we just look at it in terms of grams, so we got here 23 right, grams upon 84 grams, which is the total, times 100, okay, which is then equal to 27.4%. And then if we want now hydrogen, which is equal to 1 upon 84 grams times 100%, and that will give us 1.2%. Then if we want carbon, that would be, we've got how much of carbon? 12. So it's 12 grams upon 84 grams, which is the total mass, times 100%, which is then equal to 14.3%. And then if we want oxygen, which is equal to, as you can see, that is 3 16s are 48, so it's 48 grams all upon 84 grams times 100%, which is then equal to 57.1%. Let's say if I have a 100 gram sample of sodium hydrogen carbonate, you can see that it's got 57.1% of oxygen, right? And comparatively, it's more than half of that mass is oxygen, right? So in a way, it is also a good source of oxygen. Right. Now let's look at the next one. Here we have copper sulfate, okay? Now in copper sulfate, let's look at it, and we say, okay, now we have copper sulfate, and we want to look at the mass of copper sulfate. So if we look at this, let's erase that. And if you see copper, so copper you can see is 63.5. Correct. Then if we're looking at sulfur, we see sulfur is 32. And oxygen is 16. Isn't it so? Right? Now, okay. So, here we had copper sulfate, so we say, alright, let's work that out. And then we have M, okay, of M of CuSO4, which is equal to, we break this up, 1 molar mass of that would imply 1 mole of Cu, right, plus 1 of S plus 4 of oxygen. Isn't it so? Right. Now, if we saw copper was 63.5 plus 32 plus 4 times 16, okay, which is equal to 63.5 plus 32 plus 64, okay, and which is equal to 159.5 grams per mole. Right. So we know what the total mass is, so then it becomes just an exercise to see what the masses of the respective elements are, right? And we can then work out the percentage composition in terms of mass. So percentage of copper is equal to, we know we got 63.5, and our total mass is 159.5. Okay, I'll just say grams there, times 100%, and that gives me 39.8%. And if you want sulfur, percentage of sulfur, okay, which is equal to, there we have 32, so it's 32 upon 159.5 grams times 100%, which gives us 20.1%. Okay, and then we want percentage of oxygen, which we got there is 64 grams, all upon 159.5 grams times 100%, and that gives us 40.1%. And we know if we add all this, it's going to add up to 100. Okay. Right, now let's look at the next one. KMNO4. Now KMNO4, if we want that, we say okay, KMNO4, we want its molar mass, so we say alright, M of KMNO4, right? And if we look at that and see, okay, there we have that, right? And let's take that and let's do that, and we see, okay, manganese we have is 55, right? And that's its relative atomic mass. And if we want potassium, potassium is 39. And oxygen, by now you should already know that is 16. Okay. So you have that, and we then look at this and we say, okay, KMNO4, which means in terms of this we have, okay, we have that is equal to K, we know, is 39, plus manganese, we saw is 55, plus oxygen is 4 times 16, right? Which is then 39, plus 55, plus 64, which gives us 158 grams per mole. Right, but we want to know now what is the percentage of potassium. So percentage of potassium of K in here is equal to, we got 39 grams all upon 158 grams times 100%, and that gives us 24.7%. And if we want manganese, we say, okay, manganese, percentage manganese is equal to, we got 55 grams upon 158 grams times 100%, which gives us 34.8%. Right. So you got that and you got that. Yeah. And then we want the percentage of oxygen in here, which is equal to, then we got 64 grams upon 158 grams times 100%, and which says that we've got 40.5%. Okay. Right. Now let's look at the next one. Potassium hydroxide. Okay, we've got potassium hydroxide, so we look at that, and we just got the mass of relative atomic mass of potassium in our previous question. So let's look at this one, and here we say, all right, we got M of KOH, which is the same as K, right? 1 mole of that plus 1 of oxygen, 1 mole of oxygen plus 1 mole of hydrogen. Right, so if I'm looking at it in terms of moles, then, if I'm looking at 1 mole of KOH, and I'm saying I've got 1 mole of K in there, and 1 mole of O in there, and 1 mole of H in there. But if I had looked at it as a molecule, then I could say, okay, I have got 1 atom of K and 1 atom of O and 1 atom of H. Okay. So this gives me 39 plus 16 plus 1, okay, and that gives us 56 grams per mole. So we know what the total mass is, but now we want to know what is the composition, mass percent composition, which means now we want percentage of K in here. We say okay, it's 39 upon 56 grams times 100%, right? And that gives me 69.6%. That's percentage potassium. Now if I say percentage of oxygen, that would be 16 grams. Okay, 16 grams upon 56 grams times 100%, and that gives me 28.6%. Okay, and then if I want percentage of hydrogen in here, say okay, that would be, we've got 1 gram upon 56 grams times 100%, and that gives me 1.8%. Right, so if we add all that up, must be 100. So what I'm in essence saying, if I've got 100 grams of potassium hydroxide, I will have 69.6 grams of potassium and 28.6 grams of oxygen and 1.8% of hydrogen in here. Okay, so that will always be the case. Remember, in our earlier discussions, we spoke about the law of constant composition. It means potassium hydroxide will always have these relative amounts in terms of mass. Right, now let's look at the next one. Here we have now eucalyptus, and normally in Australia they have what the Aborigines used to do. They used to use this eucalyptus tree, and they then used to use the leaves to alleviate sore throats. Right? It has menthol in it. A lot of chemistry discoveries are because of natural plants that were used for medicinal purposes and things like that. But the primary ingredient of eucalyptus is eucalyptol. Right? The analysis of a sample of eucalyptol and if we take a mass of 3.16 grams, right? So we got a sample of 3.16 grams, and when its composition was analyzed, it was found that of the 3.16 grams, 2.46 was carbon, 0.373 grams was hydrogen, and 0.32 grams 0.329 grams was of oxygen of that 3.16 grams, right? So there you have this, and now what do we need? We need to determine the mass of each element in eucalyptol, right? Given those masses there. So whether we had 100-gram sample or 200-gram sample, we would get the same percentage composition, right? Which means now we know we've got 3.16 grams, but we want percentage of carbon. If we want percentage of carbon, we know carbon is 2.46 grams all upon 3.16 grams times 100, okay, percent, which is then equal to 77.8%. And if you want to know now percentage of hydrogen, that would be 0.373 grams upon 3.16 grams times 100%, and that would give us 11.8%. Right, and then if we want oxygen in here, which is equal to 0.329, 0.329 grams all upon 3.16 grams, right, times 100%, which then gives us 10.4%, right? And if we look at this should be 100. So which essentially says if I have a 100-gram sample, right, and you could see in the sample when I had 3.16 grams, I got 2.46 grams of carbon and 0.373 grams of hydrogen and 0.329 grams of oxygen. But if I had a 100-gram sample, I would have had 77.8 grams of carbon, 11.8 grams of hydrogen, and I would have 10.4 grams of oxygen. Right, so here what we have is that we were given the formula of a compound and we needed to determine its percent composition in terms of mass. Right. Okay, now we're doing the reverse. Here you are given the percentage mass, right? And we need to determine the empirical formula. Right, so in a previous exercise, a previous section here, we were given the formula and we determined the percentage composition. So here, what's happening is we are given the percentage composition and we determine the formula. So we need to go through certain steps, which you'll see. Right. So here now, we have the empirical formula. So what's an empirical formula? Empirical formula is the simplest formula, right? What does that mean? I'll explain to you now. Firstly, also an empirical formula is determined by experiment and by observation, right? And here, what does the empirical formula do? It shows us the relative number of atoms of each element in a compound using the simplest whole number ratio. Simplest whole number subscripts, right? Subscripts, it's like when I say if I say N A2SO4, these are the subscripts, okay? SO4, that means there's a subscripts. We need to know what the subscripts are in these empirical formulas, and we need to have the whole number ratio of these. So an empirical formula is unlike a molecular formula. Molecular formula is one where you got the actual number of atoms of respective elements within a particular molecule. But the empirical formula is we need to have the simplest whole number ratio. Okay. So here we have now the empirical formula of a compound is determined from mass percentage, composition, and the molar masses of the elements present. So we need to have the molar masses and the mass percentage. Once we know the mass percentage, we need to know the molar masses of the elements in order to work out empirical formula. Okay, now, here I've just brought this in so that you are aware of the experimental techniques that are available in order to determine the empirical formula, but I'm showing you this one here. This is called combustion analysis, right? There are several techniques to determine empirical formula, but I am showing you this one, right? Just to give you an idea, so that you have a sense of how empirical formulas are determined. Now here is what we have, is a combustion analysis. Combustion, when something combines with oxygen, it combusts. And what it does, if it's a hydrocarbon, it gives off carbon dioxide and water. So here we have a sample. Here's oxygen being pumped in. Here we have a sample, right? And this is a sample. The mass of it, or the empirical formula, you don't know. But what you do know, okay, it's made of carbon. We don't know how much of carbon, so we say X of carbon. And we know it's made of hydrogen. We don't know how much of hydrogen, so we say Y of hydrogen. And we know it's made of oxygen, but we don't know how much of oxygen, so we don't know those subscripts, so we need to determine them. But this is one way in which they do it. Let's just take you through this quickly. So, for instance, if I have a compound, which is now, here in this case, I've got it as C2H6NO. So let's, okay, so, but you didn't know what this compound is, right? You just know that it's got carbon, hydrogen, and oxygen. So we say, all right. Then we say, okay, but it combusts. So that means I'm adding oxygen in here. So it's in a furnace, right? And it's heated. And when it's heated, this molecule breaks down. And what does it break down into? It breaks down into carbon dioxide, and it breaks down into water. So it breaks down into these components. And okay, so we balance this reaction, and we balance it, okay, and there is balance, okay. But the point I want to illustrate is, now you see the carbon dioxide gets collected here in this carbon dioxide absorber. The water gets absorbed in this absorber here. So if we now get the masses, if we get the mass of CO2, right, we get the mass of CO2 in this carbon dioxide absorber there, and we get the mass of water in the water absorber, we can then work backward, because if we know the mass of carbon dioxide that's produced, if we know the mass of carbon dioxide is produced, we can indirectly get the mass of carbon that was in the sample. The same thing happens with hydrogen. If we know the mass of hydrogen that's produced, then we can get the mass of hydrogen in this particular sample. And then we can work out how much carbon, hydrogen, and oxygen is in that particular sample, and that gives us the empirical formula. You will notice here, which is not directly relevant, but I will indicate this, that here you see is also copper oxide, right? So you may say to yourself, but why have we got copper oxide here? Now copper oxide is actually it's oxidizing agent. It's an oxidizing agent. So what happens is it say for instance, when carbon dioxide is burnt in a furnace, when the sample is burnt in this furnace, what can happen is that sometimes you don't get carbon dioxide, you may get carbon monoxide, or you may even get carbon, right? So when that happens, you are not going to get these samples in the carbon dioxide absorber. So what the copper oxide actually does is that it oxidizes the carbon. Okay, it oxidizes it, and we dealt with red very, very briefly, but we spoke about redox reactions. And so the carbon then gets converted to CO2, and the carbon monoxide also to CO2. So we know that everything here gets captured in this absorber, and we want everything to be captured in that absorber because then we know how much carbon was in that particular sample. Right. Okay, so that's just to give you an illustration of how that works. Sometimes we talk about empirical formulas without giving you experimentally how it's done, and it just becomes a bit more difficult. Right, now what we have here is we are given the mass, okay? The mass percentage of a compound, and we need to determine the empirical formula. So this particular compound we know contains mercury, and how much of it? 73.9%. And it contains carbon, and how much of it? 26.1% of chlorine. Right. 26.9%. 26.1% of chlorine and 73.9% of mercury. So we know if we given a mass percentage like that, we can then assume 100 gram sample. So we say assume a 100 gram sample. Okay, you could assume a 200 gram sample or a 50 gram sample, whatever, but since it's percentage, we will assume 100 gram sample, right? So we say, okay, we have Hg, right, which is 73.9%, and we have chlorine, which is equal to 26.1%, right? And we know we have HgCl, but we don't know how much we have of Hg, and we don't know how much we have of Cl. Alright, those subscripts we don't know. All we know is it has Hg and and so it has mercury and it has chlorine. Okay, and now if we want to determine, so we need to determine the mole of each element, right? We need to determine the mole, right, of each element. Okay, and so we say, okay, let's see if, so here we got this, we assume 100 gram sample, which means we now assume that Hg we got 73.9 grams, and that we got 26.1 gram. So need to determine the mole of each element. Okay, so now let's see. We say, okay, N of Hg is equal to 73.9 grams, correct, over the mole of this would be, if you look at the mass, you'll see is 201 grams per mole, right, of mercury. In the periodic table, it's 201 grams per mole, and which gives us now 0.37 mole. Okay. Right, and we want to know what is N of Cl, which would be equal to 26.1 gram all upon, but then we look at the moles of molar mass of chlorine, which says, and that maybe I should just do, alright, I'll do it here. Moles of chlorine, or the mass of chlorine, over the molar mass, which is 35.5 grams per mole, right? Per mole, and that gives us 0.74 moles. Okay, so what are we saying here? We are saying we have 0.37 moles of that. Okay, we got 0.37 moles of that and 0.74 of that. So we say N of Hg, correct, is to N of Cl, which means I have 0.37 of this, and I have 0.74 moles of this. Right, so if we want the lowest ratio, then we divide throughout by 0.37. And we divide throughout by 0.37, we have 0.37 divided by 0.37, and here and there we have 0.74 divided by 0.37. Which means we now have, and so that is equal to that, and that is equal to 1 is to 2. There you have that. Which would then mean if I take Hg, I've got 1 of it, and Cl, I've got 2 of that. So it means HgCl2 is the empirical formula of this particular compound. Right. Now, let's look at the next one. We did this, we know what the formula was. Remember, we did it earlier, and the formula for this was, if you remember, all right, but let's work it out, because this we were given the formula and we had to work out the mass percentage. But here now, you're given the mass percentage and you have to work out the formula. So we say, all right, what is this formula? I say, okay, we have iron and oxygen, so I don't know what's that, and oxygen, we don't know what's that, but we have to determine it given this. So we say, okay, we got Fe, right, is equal to 70%, correct? And oxygen is equal to 30%, isn't it? So we say assume 100-gram sample. Right, we assume 100-gram sample. So if we assume 100-gram sample, we can then say we then have 70 grams of iron, and we have 30 grams of oxygen, right? So 70 grams of iron Fe and 30 grams of oxygen, right? If we assume that. So we can say, therefore, I've done it there on top, but therefore mass of Fe is equal to 70 grams and mass of oxygen, right, is equal to 30 grams. Okay, I'm looking at oxygen, 30 grams. Right. So if we look at this here now, we say, okay, now we need to determine the moles of iron. So if we want to know the mole of iron, it would be the mass, isn't it? I didn't do this in the previous one, but I thought let me write it out here, which is better, upon the molar mass, which would mean the mass we got is 70 grams, all upon, we know that the molar mass is 56 grams per mole, right, per mole, and that gives us what? Gives us 1.25 moles. That is what it gives us. Okay. And if we look at N of oxygen, N of N of oxygen, and that is equal to 30 grams, right, all upon each molar mass, at which I could maybe also do it here. So mass over the molar mass of oxygen, which is equal to 30 grams, okay, all upon 16 grams per mole, right, and that gives us 1.875 moles. Okay. Right, so you got the mole, the relative amounts in terms of moles. Okay? So we say, all right, now we have N of Fe is to N of O. Right? Which then means we got 1.25 is to 1.875. Isn't it so? Right. And we need to get the smallest ratio, so we say divide by 1.25. So we divide this by 1.25, and that, which means if we divide this by 1.25 and divide that by 1.25, then we end up with 1 is to 1.5. Alright, so you can see now 1 is to 1.5, but that is not the simplest whole number ratio. So what we do is we want to get the simplest whole number ratio, so we now multiply throughout by 2, and that gives us 2 is to 3. Alright, there's the simplest whole number ratio. Okay? And here we then say, okay, then I have Fe. How much have I got of it? 2. And oxygen, what's the mole ratio? 3. And you saw when we started off, iron oxide, that is its empirical formula. Right, that you could have did that. Okay? You could have even perhaps, if you wanted to, you could have did this in fraction forms, right? Which means if you want to, you could have said, okay, 1.25 is the same as 1 1/4, and 1 1/4 is equal to 5/4, right? And 1.75 is the same as 1 7/8, right? So that's the same as 1 7/8, which is equal to 15/8. See, you could have it in fractions if you wanted to, and then you could solve that, which would mean you would have then had, let's just say, if we wanted to, we could have said Fe, right, is to O, which is 5/4. 5/4 is to 15/8. Right, 15/8. Which means now, if we wanted to, I could then multiply both by, so I could multiply, so we got here, let's say, I multiply, so we got F there, 5/4, if I multiply it, I could have it as 10/8, correct? And is to 15/8, right? Since the denominators are the same, this would then imply I have 10/10 is to 15. 10 is to 15, which is the same as 2 is to 3. Right, it's an alternative way that I did this, just to show you. Sometimes I like to leave it in fraction form. Right, so there you have that one. Now, let's look at the next one. Here we have determine the empirical formula of the compound with the following percentage composition. Right, and here we got 57.5% sodium and we got 40% oxygen, and we got 2.5% hydrogen. Right? If you can see this formula, it's got Na, it's got O, and it's H. And if you know, you will already be able to recognize what its empirical formula is. But let's do it. So N of Na is equal to, we got 57.5 grams, right? Right, so here I'm not saying assume, I could just, perhaps maybe let's just do that, right? We say, okay, assume 100-gram sample. Right. Therefore, Na is equal to 57.5 grams. Right. And oxygen is equal to 40 grams, and hydrogen is equal to 2.5 grams. Okay, so if you want to work out now N of Na, which would be 57.5 grams, right? All upon the molar mass of it, 23 grams per mole, which tells me that's equal to 2.5 moles. Look at the next one, N of oxygen, which is 40 grams. And oxygen we know is 16 grams per mole. And what does that give us? It also gives us 2.5 moles. Okay. And then we say N of hydrogen. How much is that? So 1 gram all upon, my apologies, it's 2.5 grams all upon 1 gram per mole, and that gives us 2.5 moles. And we know if we divide all of these by 2.5, right? If we divide by 2.5, then what do we get here? Here we would get 1 mole. There we would get 1 mole. And here we would get 1 mole. Each one 1 mole. So what would the formula be? It would be Na1, O1, and H1. Right. Divide throughout. Okay, so here you got 2.5 and you divide throughout by 2.5, you get 1 mole, and there we have that. Okay. Let's look at the next one now. Here, and you know sodium hydroxide is NaOH, and that is your simplest ratio for NaOH. Now let's look at KClO3. KClO3, here we got 32%, 29% of chlorine, and 39% of oxygen. Okay, so if we want it in terms of mass, so we say assume, okay, assume a 100-gram sample. Right. If we assume a 100-gram sample, then K is equal to 32 grams, right? and chlorine is equal to 29 grams, right? And oxygen is equal to 39 grams. 39 grams. Okay, so we assuming that we got 100-gram sample. But now we want to know in terms of moles how much each. So we got N is equal to KCl, and we got 32 grams all upon potassium, what am I doing, of K, right, of K, and we know that is 39 grams per mole, which then equals to 0.82 moles. Right. And if you look at the next one, we got N of Cl, which would be, we got 29 grams, so it's 29 grams, all upon chlorine we know is 35.5 grams per mole, right? Which is then equal to also 0.82 moles. Okay. So if you look at that, and now we want oxygen, N of oxygen is equal to 39 grams, right? All upon 16 grams per mole, and that gives us 0. Not 0 point, gives us okay, 2.4 moles. Okay. Alright, so you got that, and you got that, and you got that. Now what do we need to do? We got the 3, so we divide throughout by, so we got K, right? And we need to divide by throughout by 0.82. Right, so which would mean if I've got K and I've got Cl and I got O here, and I'm dividing throughout by 0.82, right? What am I going to have? I'm going to so I'm divided by then 0.82, and I'm going to divide that by 0.82, and I'm going to divide that by 0.82. If I divide all that by 0.82, I'm going to have 1, and I'm going to have 1, and 2.4 divided by 0.82 is 3. Which means, what does my formula become? My formula becomes K, remember, K, X, C, L, Y, O, Z. Right. And K would be 1, right? And Cl would be 1, so it would be K. Let's take that away, yeah. Right, so K would be 1, Cl would be 1, and oxygen would be 3. So that's the empirical formula for potassium chlorate. Right, so that's the formula for potassium chlorate. Okay. Alright. Now let's look at the next one. Here it says, determine the chemical formulas from the following analysis. Right? And we want to know the chemical formula from the following mass percentage composition. So what happened here, we are given the and this is a fertilizer which is found to have the following mass percentages. Okay, so again we have this, and we look at we say assume. Okay, we say assume a 100-gram sample. Okay, if we assume a 100-gram sample, okay, that means N is equal to 12.2 grams, hydrogen is equal to 5.26 grams, phosphorus is equal to 26.9 grams, and oxygen is equal to 55.6 grams. It's 55.6 grams, right? So we've converted that to grams, but we now need to determine the moles, right? So if you want to know the moles, we say okay, N, same exercise we're going through again, right? So N of nitrogen would be N of nitrogen is equal to 12.2 grams, all upon nitrogen. Molar mass is 14 gram per mole, and that gives us 0.87 moles. Right. And N of hydrogen is equal to 5.26 grams, and the molar mass of hydrogen is 1 gram per mole, and that gives us 5.26 moles. And then you want phosphorus. N of P is equal to 26.9 grams. This 26.9 grams, all upon phosphorus is 31 grams per mole, and that gives us 0.87 moles. Then we look at oxygen. That would be 55.6 grams, all upon 16 grams per mole, and which is then equal to 3.46 moles. Okay, so we have that so far. But now, what do we want to do? We want to divide this by the smallest value, right? Which would mean if I have so say N, we have N mole there is to N of H is to N of P is to N of O, isn't it so? Which would mean we got 0.87, right? And we got 5.26, we got 5.26, we got 0.87, and we got 3.46, right? So we divide throughout by 0.87. If we divide throughout by 0.87, which means 0.87, 0.87, okay, and 0.87, right, which would mean we then, and this implies or gives us, that gives us 1, right, this gives us 6, okay, it's 6.01, so we round it off to 1, right, and so that gives us 6.01, and this gives us 1, and this gives me 3.97, right? So if we round this off, it's 1, it's 6, is 1, and that is equal to 4. And if we look at that, which means N is 1 of it, H, right, is 6 of it, phosphorus is 1 of it, and oxygen is 4 of it. So this is the empirical formula for that fertilizer, NH6PO4. But you can also verify it. You can verify it because you can work out the molar mass of NH6PO4. And the molar mass of NH6PO4 is equal to, I'll just put it down here, 115.02 grams per mole. Right, that is the molar mass of this fertilizer. And if you want to determine what is the mass of nitrogen in this particular compound, you know how to work in reverse, because there's the total mass. You know the mass going to be 14 grams, and you would then say 14, you would then take 14 grams upon this mass here, right? Means if you now want to work out the percentage of nitrogen in this, and also to verify if the formula is correct. So you take that, and when you want to work out the percentage, what should you get? You should get 12.2%, which means you need to take the mass in that sample, which is 14 grams, upon 115.02, and that should give you 12.2%. You know, like, I mean, okay, maybe let's just illustrate it. If I wanted nitrogen's percentage composition, that would be is equal to, we know nitrogen in here is 14 grams, right? All upon 115.02 times 100%, and what do I get? I get 12.2%, right? Which is there, I get 12.2%, just to illustrate this one. Okay, 12.2%. Okay, that helps, because sometimes if you're not sure if your formula is right, you just double check and check your percentage composition, then you say, okay, that's fine. And you know, you have that. Right now, looking at the next one, we need to determine the empirical formula of saccharin. That is actually a sweetening agent and has this mass composition, right? It has this mass composition, so we say okay. If you look at this now, so again we go through the same routine, right? Which means if we now have others and we say determine the empirical formula for saccharin, a sweetening agent has a mass composition, right? So same thing we say again, we say assume a 100-gram sample. So if you assume the 100-gram sample, then we know that this percentage here would imply 45.89 grams. That would be 2.75 grams. This would be 7.65 grams. That would be 26.20 grams, and that would be 17.50 grams. Okay, so there you have that. We got the masses. If we assume a 100-gram sample, okay, so let's maybe just do this. We can just say here, maybe there, and say here we can say right, assume a 100-gram sample. Right, so you converted it to. Now we say okay, we want N of carbon is equal to 45.89, right, grams, all upon 12 grams per mole, since we're dealing with carbon, and that gives us 3, that gives us 3.8 moles. Then we have N of H, which is equal to 2.75 grams, all upon 1 gram per mole, right? And that I've just rounded it off there to 2.8 moles. Could have left it as that, right? And then N is equal to 7.65 grams, all upon, we know nitrogen is 14 grams per mole, and that gives us 0.55 moles. That it's nitrogen, so that's nitrogen, and then N of oxygen is equal to 26.20 grams, because there's the mass we have, upon 16 grams per mole, and that gives us 1.6 moles. Okay, and then we have N of sulfur. Right, the saccharine actually even contains sulfur. Right, which means it's equal to 17.50 grams, all upon 32 grams per mole, and that gives us 0.55 moles. Okay, so there we have the respective moles of each one, but we want to now get the simplest ratio. So what do? We see our smallest value is 0.55, so we divide throughout by 0.55, right? So when we divide by 0.55, so we say divide by 0.55, where we also divide by 0.55, and when we divide this by 0.55, that is equal to 7, right? And if we take this and divide by 0.55, right, that gives us 5. Okay, and this one, if we divide by 0.55, right, I've rounded some of these off. Right, okay, so nitrogen, and if we divide that by 0.55, that gives us 1, and if we divide this by 0.55, that gives us 3, right? And if we divide this by 0.55, 0.55, and that gives us 1. Okay, 1. So if you look at this, you've got carbon, hydrogen, nitrogen, oxygen, and sulfur, right? So it's carbon, hydrogen, nitrogen, oxygen, and sulfur. Okay, which you then and sulfur. And if you look at this, how much we have here, right? The ratio 7. So it's 75131, right? So it's 7, 5, 1 we don't have to put, and 3, 1. So that's the empirical formula of saccharine. Right, and you can verify it. I mean, like I did with the other example, you can verify it and check whether the percentage compositions are correct. You just need to determine the molar mass of this. Right, now let's go to the next one. Here we got L-DOPA. It's a drug, right? And what's it used for? It's used for Parkinson's disease, right? Same routine we're going through here again, and we want to know what is the empirical formula, right? So we can do the same thing, and we can say here assume, okay, a 100-gram sample. If we assume a 100-gram sample, then we know that we got 54.82 grams of carbon, we got 5.62 grams of hydrogen, and we got 7.10 grams of nitrogen, and we got 32.46 grams of oxygen. Once we have this, we go again through the same routine, and we say, okay, N of carbon would be 54.82 grams all upon 12 grams per mole. Right, 12 grams per mole. And that is equal to 4.56 moles. Then we have N of H, which is 5.62 grams all upon 1 gram per mole, and that would be 5.62 moles. Okay, and then we have hydrogen N of nitrogen, which is equal to 7.10 grams all upon 14 grams per mole, which then gives us 0.51 moles. Right, and then we have N of oxygen, which is 32.46 grams, right, all upon 16 grams per mole, which then gives us 2.02 moles, right? So what we do here, again the same thing, divide throughout. So we divide this by 0.51, right, mole, and that would give us 9 moles. Here we divide that again by 0.51 moles, and that would then give us 11 moles. And we divide this by 0.51, and that would give us 1, right, mole. Okay, and then we've got this divide by 0.51. Okay, so divide by 0.51. Divide by 0.51, and that gives us 4 moles, right, which I've rounded off. It comes to actually 3.96. And if we look at this, then we've got C, we got H, we got N, and we got O, right? So here we got 9, and 11, right, and 1 and 4. So if we look at this, it would be C9, H11, N1, and O4. Okay, that is a empirical formula for this compound. And again, you can check the mass. If you look at the total mass, you could say, okay, what would the total mass of this be? You would say, all right, 9 times 12 plus 11 times 1 plus 14 plus 4 times 16, and you add all that up, and what does it give you? It gives you 197 grams per mole. That's what it gives you. And if you want to now test whether the percent composition of carbon is equal to 54.82%, you can then test it, okay? Because then you know carbon, how much have you got of it? You've got 9, 12, so 108 grams of carbon, right? All upon the molar mass of the sample, which is 197, right? Times 100%. And what does it give you? It would give you then 54.82%. Right, which would then be equal to 54.82%, which gives you an indication also that your empirical formula seems to be on track. Right, now let's look at the next one here. We have now a slightly different question. Right, it says the molar mass of vitamin C. Here the molar mass is given, right, of vitamin C. This is the actual mass of that molecule. But the empirical formula is this. Right, now remember we said the empirical formula is a formula that we get via experiment, right? And that gives you the lowest whole number ratio. Right, so sometimes the empirical formula can be the molecular formula, but sometimes the molecular formula is a multiple of the empirical formula. Okay, so if we look at this, we say we know that the molar mass of this particular sample, okay, we don't know what it is. It could be CX, H, Y, and O, Z, right? That's the molecular formula. But what we do know, that is 176.12 grams per mole. That is what it is, right? But the empirical formula here, okay, is telling us, okay, which we have C3H4O3. That's the empirical formula. So what is the molar mass of this one? So the mass of this empirical formula C3H4O3 is equal to, here we say 3 times 16 plus 4 times 1 plus 3 times 16. That's not 16, that is 12. Okay, 12, and that gives us 36 plus 4 plus 48, isn't it so? Which gives us 83 8 grams per mole. Right, so the empirical formula, when we did determine that, it's telling us that the formula is 88 grams per mole. Correct? But the molecular formula indicates no, the mass is actually 176.12. Right, but we want to now determine what the molecular formula is. So we say, all right, we can say molecular formula. Right, I will abbreviate it. I say molecular formula, right, which is CXHYOZ, right? Over the empirical formula, which is C3H4O3, and we say, okay, that is equal to, we know the molecular formula mass is 176.12 grams per mole, but the empirical formula is 88 grams per mole, right, which says that the molecular formula over the empirical formula is equal to 2. Right, because that 88 goes into 176.12 twice, right? And if we look at that, which is equivalent to, let's just rather just say, yeah, okay, and it's equivalent to 2, right? So which means molecular formula is equal to 2 times the empirical formula, right? And which means it's equal to 2 times, what's my empirical formula? It's C6, sorry, I made a mistake here. That's C3, that's C3, right? H4O3. So which means, sorry about that. So it's C3, H4, right? O3. And if I multiply throughout by that, so it becomes C6, right? H8, right? And O6. So that is my molecular formula. And you can double check that. You say, okay, M of C6H8O6, what is it? We say, all right, 6 times 12 plus 8 times 1, right, plus 6 times 16. And when you look at that, that gives you 176 grams per mole. Right. So you can determine the molecular formula given the empirical formula. So you can see the molecular formula here is given C6H6O6, and that is not the simplest ratio, right? So you've got C6H8O6. What would the simplest ratio be? You have to divide all this by 2. So you divide that by 2, you divide that by 2, you divide that by 2. So you got C3H4O3. That is your empirical formula, right? It's the lowest whole number ratio, right? So, and that is your molecular formula, and that's your empirical formula. Okay, there you have it, and see you next time.